Alright everyone, so I guess we'll get started. Anyway, the beginning of the tutorial is a bit slow, somewhat more introduction, so even if people join in later, it's going to be fine. So first of all, thanks everyone for coming to this tutorial. I am Nisarg Shah. I am an assistant professor at the University of Toronto. I'll be delivering the first half of the tutorial until the coffee break at 3:30. And then Rupert Freeman, who is a postdoctoral fellow at Microsoft Research New York, will take over. Okay, so before we start, some disclaimers as to what this tutorial will be and will not be. So in this tutorial, first of all, we will not assume any prior knowledge of fair division. So just as a show of hands, how many of you sort of know about the field of fair division, have heard of envy-freeness, cake cutting, proportionality, Pareto optimality, definitions like that? Okay, and how many of you have not heard of these definitions? Okay, so hopefully we'll have enough sort of that both groups can derive some value from. Because we have a very sort of ambitious goal in front of us to review the entire literature on fair division, we will not be able to walk through any tedious detailed proofs. I anyway personally don't like doing that in time limited tutorials, so this is hopefully going to be more fun, but we'll have pointers to all the papers that we refer to. So if you are interested in some of the proof techniques, you can just pull up those papers and look for the techniques. Another thing we'll not do is we'll not claim to present a very complete overview of the entire field of fair division, because it's a pretty huge field and there have been progress on many different frontiers. So we'll rather select a number of subfields through which we can create a coherent story, and then we'll present a detailed, hopefully detailed overview of only those subfields. But we'll also have, towards the end of each part of the tutorial, we'll also have some pointers to a number of sort of subfields that we have not covered, and some basic results in those areas. Because we have a lot of time, just feel free to interrupt me at any point if you have any questions, if something that I'm saying is not very clear, or if you want a further explanation as to how that happens. As I already mentioned, we'll just select the case of additive preferences for most of the tutorial. As I go forward, I'll mention what that is and present results on that, but we'll also have some pointers to results on non-additive preferences. And another thing that we don't claim is for this tutorial to be 100% error free. So some of the results that we have cited here, for example, they might have been presented in some earlier papers that we might have missed, or some of the problems that we mentioned as open problems in this tutorial might even have been resolved in some recent papers that that did not come up in our literature review. So if you spot any errors, any missing results that you think go nicely with the story, or any incorrect attributions, feel free to email us during or after the tutorial in one of these two emails. At the end of the tutorial, we are planning to post the slides online on the tutorial website. So you'll always have access to these slides, including these emails, and we can post the corrected versions of the slides online. Okay, so with the disclaimers out of the way, let's go through just a brief outline of what we are going to see in this tutorial. So we'll look at a bunch of different fairness axioms, and this includes proportionality, envy-freeness, maximum share guarantee. These are so-called individual notions of fairness that look at what each individual deserves to get and try to give each individual their sort of fair share. There are also some group-wise notions of fairness, and this has been becoming more and more studied recently. And this includes the core, group envy-freeness, group-wise maximum share, and group fairness. So we are going to look at that. After looking at fairness properties, we are going to look at the implications of satisfying these fairness properties. And specifically, we are going to look at the literature on price of fairness, the interplay of these fairness properties with other properties that we want, for example, incentive compatibility or strategy proofness. and Pareto optimality. And we are also going to look at sort of what happens when you look at some restricted settings where you can sometimes achieve more than what you can achieve in the general setting. And mentioning settings, we'll look at three specific settings that have been very well studied in the past several decades. And this is cake cutting, division of homogeneous divisible goods, and allocation of indivisible goods. And as I go through each setting, I'll formally describe what the setting is and how we can, the allocation algorithms for those settings. Alright, so before we go into any individual setting, let's just take a generic overview of what a standard sort of fair resource allocation problem looks like. So you have a set of agents, we'll usually denote this by capital N, and the individual agents by numbers 1, 2, ... small n, so small n is the number of agents. We'll have a set of resources that we want to divide among these agents, we'll typically denote this by capital N, and this may be finite or it may be infinite. Now these agents will have some preferences over these resources. Some agents would prefer some resources more than some other resources, and we will typically denote these preferences by valuation functions. So in particular, agent I will have a valuation function called Vi, and this goes from, this assigns a real value to each subset of the set of resources, right? So this essentially says if agent I is given this subset of the resources, what is the value that agent I derives from this subset. Now this is sometimes called cardinal valuations because it assigns sort of a real value to each potential allocation that the agent might receive. There are other ways of looking at preferences of the agents in the literature, like ordinal valuations, but for the most part of the tutorial we will stick to cardinal valuations. Here I've used the range as R, the set of all real numbers. But in some cases the range might be R plus. This happens when the resources are goods, things that the agents want to get. So they'll have non-negative values for that. In some cases the resources might be bads or chores that the agents want to avoid. In those cases the values might be non-positive or from R minus. And finally, the final piece of the framework is going to be allocations. So each allocation is denoted by A, that is a vector of A1 through AN, where AI is the subset of resources allocated to agent I. And typically we would want a partition of the resources among the set of agents. So we will want that the same resource is not allocated to two different agents. So we will want AI intersection AJ to be empty set. And typically we would want to allocate all the resources. So we want the union of all the AIs to be the set of all resources M. And we will sometimes refer to this as complete allocation when we want to draw a contrast to a partial allocation where the union of AIs may not be equal to M, right? But whenever we don't mention this, assume that it's a complete allocation. Okay, so any questions so far? Okay, so let's start with the first setting that's called cake cutting. This was, fairness is a concept that has been thought about for many centuries. But its formal sort of axiomatic foundations were laid down by Hugo Steinhaus in 1948 with this setting of cake cutting. And so here you again have this set of agents. You have a resource which is a cake, and typically in most of this literature it's denoted by this unit interval 0 to 1. Now a cake could be something more general. For example, you can have a square, or you can have a 3D cake, or you can have a 4D cake, but for most existential results, you can actually draw one-to-one mapping to the unit interval 0 to 1. So these sort of for the existential results, this is typically without loss of generality. Now when you do these mappings are sometimes weird, and they may not preserve the nice properties of the allocations. So for example, if you have a unit square and if you cut it across a diagonal, then you have these nice two triangle looking pieces. If you draw one-to-one mapping, a one-to-one bijection to this unit interval 0 to 1, that bijection may completely throw up the nice looking sort of geometric properties of the allocation. So when you are interested in that, you may actually want to work with cakes that are explicitly not the unit interval, but here we'll sort of restrict our attention to this case. And finally, we'll want some constraints on the allocation for the problem to be sort of very easily defined. And specifically, we want the allocation of each agent I, AI, to be a finite union of disjoint intervals. So we don't want to chop up our cake in infinitely many pieces and then sort of arrange this infinitely many intervals around. We only want to chop up our cake in finitely many pieces and then rearrange these intervals to create allocations. So for example, agent I can be assigned the subinterval from 0 to 0.1, union the subinterval from 0.5 to 0.6, union the subinterval from 0.8 to 1. But you only want a finite union, not an infinite union. And sometimes we will want allocations that are even more constrained, namely simple allocations, where we only chop up the cake at n minus 1 pieces. So that creates n intervals, and then we just take each interval and assign it to one agent, right? So each agent gets a connected single interval as the allocation, and we'll call these simple allocations. Okay, with the basic setup out of the way, let's look at how the agents represent their preferences over different parts of the cake. So each agent I has an integrable density function denoted fi, which goes from the unit interval to the positive reals or the non-negative reals. And if you want to find out what is the value that agent I places on some piece of the cake, so this piece x, again remember, is a finite union of disjoint intervals, all you do is you just integrate the density function over this piece of the cake. So think of this fi as the PDF of a probability distribution, and if you want to find sort of the probability placed on some interval, you can just take the integration of the PDF. Right? Now for some normalization reasons, we would want to require the integral of over the entire cake to be 1, right? So we want the value that each agent places on the entire cake to be 1. Now for most part, this is going to be without loss of generality. Many of the fairness properties that we define can be defined for non-normalized valuations, and the same protocols carry over, but for some other analysis we'll actually use this normalized valuations. So let's just go ahead and assume this right away. Yes?
Are you assuming that the agents have different preferences over different parts of the cake?
Yes, that's true. So the agents have different preferences over different parts of the cake. So some agent may actually want some part of the cake less and some other part of the cake more, and for other agents the preferences could be reversed, and we'll see examples of that.
How does normalization, how does it not with generality? One agent may want to take twice more value.
Right. So for example, one property that we'll look at, and this is probably going to come up pretty soon, one property that we'll look at is that each agent should get at least an nth of the value that they place on the entire cake, right? So if you place twice as much value on the entire cake, the property still does not change, right? All you are doing is you are getting an nth of the total value that you place. So if you just normalize all the valuations up front, that's still not going to change the allocations. And most of the algorithms or the protocols that we'll see are also sort of, they'll work with normalized valuations. So if you feed unnormalized valuations, you can first just normalize the valuations. You can divide the valuation of each agent by the total value that they place on the cake, so that the new total value becomes 1, and then you run the protocols. Okay, so you can't actually get more of the cake just by saying that you like the cake much more. Okay, so now this is a sort of a restricted model. There are less restricted models for cake cutting, but we'll not get into all that details. If you have this model, then three important properties follow immediately. One is this normalized valuations. This follows just from this sort of normalization that we assumed on the last slide. But the important property is divisibility. So let's say you have an interval x to y, and the agent I places a certain value on this interval x to y. Now you want to find an interval for which agent I has value that is exactly lambda fraction of his value for the whole interval x to y. This property says that you can always find a point z such that agent I's value from x to z is exactly lambda fraction of his value from x to y, right? And this follows again sort of from the properties of integration, and this is going to be very crucial in many of the results that we'll derive. Okay, so you can, if I ask the agent to chop up the cake at exactly the point where his value for the left part is equal to his value for the right part, there is always going to be such a point, right? His value for the part to the left of a point is not suddenly going to jump. And another property that follows immediately from integration is that the preferences are additive. So if you have two disjoint intervals I and I prime, then the agent's value for their union is just the sum of the agent's values for the individual intervals. Yeah. All right. And the final piece of the framework is looking at complexity of the algorithms. So in this case, so usually in computer science, when we talk about computational complexity, we mention the running time as a function of the length of the input. Now in this case, our inputs are functions. Either they are VIs or they are FIs. In either case, they are functions. And in the worst case, they could require infinitely many bits to fully represent these inputs. So instead of looking at the sort of the computational complexity, we will often talk about the query complexity, where we will have access to these functions not as sort of complete representations, but through some sort of queries that we can make to these functions. And one standard model for doing this is the Robertson-Webb model, where you are allowed to make two types of queries to each agent's valuation function. So to agent I, you can pass two numbers x and y, and you can ask her, what is your value for the interval from x to y, right? And agent I will just return this value. So this is called an eval query or an evaluation query. Or you can ask sort of an inverse query called the cut query, where instead of passing x and y and getting sort of this value alpha, you can pass x and alpha, and you can ask the agent, what is the point y such that your value from x to y is equal to alpha? And if there is no such y, meaning that if even the value from x to 1 is still not alpha, then the agent will just return 1, otherwise the agent will return such an alpha. So is the model clear? Okay, so let's look at the kind of fairness properties that we want from this, this setting. So the first and sort of the property that was also proposed the earliest is called proportionality. Sometimes it's called fair share guarantee, sometimes it's just called a fair allocation. And in shorthand, we will denote this by prop. This says that the value that each agent gets for their own piece of the cake should be at least 1 over n. Again, if the valuations are non-normalized, then you, instead of this 1 in the numerator, you want to put the value that the agent places on the entire cake. Okay, so what is the motivation behind this property? Well, the way agent I sees this scenario is that she has the value of 1 for the entire cake, and there are n agents between which the cake is being divided, so she is entitled to get a value of 1 over n according to her valuation function, right? But the valuation functions of different agents are different, so you can't just chop up the cake in equal lengths and then just give these lengths, give this sort of 1 over n length intervals to the different agents, because the value for that 1 over n length interval might actually be less than 1 over n. So you still need to do something slightly more intelligent to achieve this property. Another property is called envy-freeness. Here, an agent doesn't just look at what they deserve to get, they also look at what the other agents are getting. And what this says is that no agent should prefer what is given to another agent over what is given to them themselves. Right? So if you look at agents I and j, the value that agent I has on their own allocation, Vi of Ai, should be at least as high as the value that agent I places on some other agent's allocation, Vi of Aj. And finally, the third property is called equitability, or EQ in short, and this simply says that each agent should have the exact same value for their own piece of the allocation, meaning that Vi of Ai should be equal to Vj of Aj for all I and j. So this says that even maybe I don't envy what you are getting, because what you are getting is very less valuable to me than what I am getting, but it's very highly valuable to you. So why is the algorithm giving much more to you of what you like than to me of what I like? And this distinction is going to be clear in the next example, where we'll look at the exact differences between these three properties. So let's look at this example. We have three agents here, and their PDFs, the density functions are plotted here. So agent 1's density function is in the red. So agent 1 likes the first 1/3 of the cake uniformly, and doesn't like the rest 2/3 of the cake at all. So she has value density 0 for the rest 2/3 of the cake, and to make the integral 1, her density for the first 1/3 of the cake has to be 3. So if you actually take the integration of this curve from 0 to 1, it's going to be 1. Now agent 2 likes the entire cake uniformly, so her density is 1 throughout the whole interval 0 to 1. And similarly, agent 3 doesn't like the first 2/3 of the cake at all and likes the last 1/3 of the cake uniformly. Okay, is the example clear? Okay. Now let's say we look at the following allocation where agent 1 is getting the interval from 0 to 1/9. Note that agent 1 wants from 0 to 1/3, so this is a third of what agent 1 actually wants. And because it's a third of the interval that agent 1 wants, her value for this allocation is going to be 1/3. Right? If she got the entire piece from 0 to 1/3, her value would have been 1, but here her value is 1/3. Similarly, agent 3 is being given 1/3 of what she wants, the interval from 8/9 to 1, so her value is also 1/3. And agent 2 gets the rest of the cake from 1/9 to 8/9. And so her value, because she just likes the whole cake uniformly, is simply the length of this interval, which is 7/9. So note that this allocation is proportional. Proportionality just requires that each agent gets a value of at least 1/n. N is 3 here, and each agent is getting at least 1/3. But this is not envy-free, because if you look at agent 1 sees that she is only getting a third of the interval that she wants, and agent 2 is getting the remaining 2/3 of the interval that she wants. So agent 1 would actually prefer to get agent 2's allocation rather than keep their own allocation. And so this is not envy-free, and equitability is also violated because equitability requires that all these three values should be exactly equal. Now here is a different allocation. Instead of giving agents 1 and 3 a third of what they want, let's give them half of what they want. Right? So agent 1 gets from 0 to 1/6, and agent 3 gets from 5/6 to 1. In this case, their value for their own piece is going to be half, and the remaining cake from 1/6 to 5/6 goes to agent 2, who has a value of 2/3 for this. Now in addition to proportionality, this is also envy-free, because if you look at agents 1 and 3, they are getting half of what they want, and agent 2 is getting half of what they want. So they are indifferent between their own allocation and agent 2's allocation. And agent 2 is certainly getting more than half of what she wants, so she certainly doesn't want to switch with agent 1 or agent 3. Okay? So this is envy-free as well, but it's still not equitable because these three values are not exactly equal. If you want equitability as well, then you have to essentially do the following allocation where agent 1 gets from 0 to 1/5, agent 3 gets from 4/5 to 1, and agent 2 gets the piece from 1/5 to 4/5. And you can check that in this case, each of them will exactly get 3/5 of the part of the cake that they want. Okay, so this is going to be proportional, envy-free, and equitable. So is the difference clear between the three properties? Yeah. Yes, it certainly can be equitable and not envy-free as well. So for example, imagine two agents. The first agent only wants the first half of the cake, and the second agent only wants the second half of the cake. If you give the first agent the second half of the cake and the second agent the first half of the cake, they each have value 0 for their own allocation. So this is equitable because Vi of Ai is equal to Vj of Aj, but it's certainly not envy-free. They would both want each other's allocation. It's not proportional, yeah. So you can have equitable that is not proportional as well. You can again create an example with 3 agents where you get proportionality, you have equitability, but you don't have envy-freeness. So actually we'll see the relations between these fairness desiderata right now. So it's actually very easy to see that envy-freeness implies proportionality, assuming that the allocation is complete. So you are allocating the entire cake. And this is simply, this can be simply seen by noting that envy-freeness requires that Vi of Ai is greater than or equal to Vi of Aj for all j. So if you actually average over all the j's, on the left hand side you still have Vi of Ai. On the right hand side you have 1/n times Vi, the total value that Vi places on all the different pieces, and that's just the 1 over n times the value of Vi for the entire cake, which is just 1 over n. So if you just average the inequalities of envy-freeness, you get proportionality. So if you have envy-freeness, you have proportionality. And for two agents, actually the reverse is also true, and this is also very easy to see. I'll skip the argument, but for two agents, proportionality and envy-freeness are equivalent, and for 3 or more agents, envy-freeness is strictly stronger than proportionality. But equitability is incomparable to both the properties. So you can have equitable allocations that are neither proportional nor envy-free, or you can have allocations that are proportional and envy-free but not equitable, or many other combinations. It has no relations to these two.
And if you add to the equitability the constraint that it should be the maximum achievable.
Right, so that the question is, what if you add just a small constraint to the equitability that somehow you want to do as good as possible? So this is called non-wastefulness, I think what you are trying to refer to. That says that you should not allocate a piece of the cake to an agent who has 0 value for it when some other agent has a positive value for it. But even then, equitability is incomparable to proportionality and envy-freeness. You can just create more examples. Okay, so once we have these 3 properties in mind, the immediate question is, can we get all 3 together? Obviously, that just means can we get envy-freeness and equitability together, because if you have envy-freeness, you also have proportionality. And the existential result for this goes actually further back than this paper, but I like this paper because it also gives some nice structure on this such an allocation. It says that assuming that the density function fi for each agent I is continuous, then we can actually cut the cake at only n square minus n places. So this creates n square minus n plus 1 intervals, and then we can rearrange these intervals to create n pieces of the cake a1 through an, such that the value that agent I places on every piece aj is exactly 1 over n. So if you look at sort of this division of the cake into n pieces a1, a2, dot 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 an, according to each agent's valuation, these n pieces are exactly the same value. And so this is called a perfect partition, and such a partition is trivially envy-free, because no matter how you assign these n pieces to the n agents, each agent gets exactly 1 over n value, and each agent's value for somebody else's allocation is also exactly 1 over n. So it's envy-free. Again, it's similarly it's equitable. Each agent has value exactly 1 over n. Yes.
So what if each tempi is like a piecewise continuous? So it's continuous exponentially.
Right. So as far as I remember, if you have piecewise continuous valuations, so essentially if you have some finite number of discontinuities, then the existential result still holds, that there exists such a valuation. But I don't think that, I'm not sure if you can still just cut the cake into n square minus n plus 1 subintervals and then reorganize those intervals. So the exact structure may be somewhat lost. All right. But this is a very nice partition. It gets everything that we at least want so far. But as we will later see, such a partition cannot be computed with any finite number of queries in the Robertson-Webb model. So you cannot place a finite number of eval and cut queries to the different agents' valuations to find such a partition. So the question is, if we don't want to shoot for everything, if we just want to shoot for individual fairness properties, can we do somewhat better? So let's start by looking at intuitively the easiest property called the proportionality. So if you have just 2 agents, there is a very nice centuries old algorithm that probably some of you might have even used with your siblings. It's called cut and choose. So the player 1 cuts the cake at a point x such that their value from 0 to x is equal to their value from x to 1, which is equal to half. So they exactly value the 2 pieces of the cake equally. And such a point x exists because of our divisibility property. Now, once player 1 does this cutting, player 2 simply chooses the piece that she prefers more. And it's easy to simulate this in Robertson-Webb model with 1 cut query from player 1 and 1 eval query to player 2. And this is clearly proportional because agent 1 gets a value of half no matter which piece agent 2 chooses. and agent 2 gets to choose the piece that she prefers more, so she also gets a value of at least half. Right? So agent 1 gets value exactly half, agent 2 gets value at least half, so this is proportional. And because for two agents proportionality is same as envy-freeness, it's also envy-free, and it requires sort of this optimal number of queries. If you can't just find a proportional allocation with only one query, you have to make at least one query to each agent's valuation. Okay, so the picture is great for two agents. What happens with more agents? Turns out that there is a very classic protocol by Dubins and Spanier, which finds a proportional allocation for any number of agents n, and intuitively the algorithm goes as follows. A referee moves a knife from left to right, starting at 0, and the referee announces to all the agents, as soon as the piece of the cake to the left of my knife becomes of value 1 over n to you, shout stop. When the first agent shouts stop, the referee cuts the cake at that point and gives that piece to the agent who shouted stop. That agent leaves, and then the referee moves forward. So without going into this, let's just see a very nice animation due to Ariel Pocaccia. So the referee starts the knife at 0, and the referee moves forward. Each agent is evaluating their value for the piece on the left until some agent shouts stop, and then the referee cuts the cake at this point, and assuming that the yellow player shouted stop, this is where the yellow player has value exactly 1/3. Imagine that there are 3 players. The yellow player has value exactly 1/3 for this part of the cake, so the yellow agent gets the cake. And then the referee moves forward, another agent shouts stop, and the referee cuts the cake there, and supposing this is the blue player gets this part of the cake, and then the remaining third red player gets the remaining part of the cake. So the reason, yes? Yes, so this protocol can very easily be gamed, at least when you know the other agents' valuations. So instead of shouting stop, where your value becomes 1/3, you can at least shout stop slightly before somebody else's valuation becomes 1/3, right? So we will look at what you can achieve when you don't want the protocol to be sort of vulnerable to this kind of gaming. But right now we don't care about that. Assuming that we have access to honest valuations, we are interested in what we can get. Okay, so clearly each of these agents, they are getting exactly 1/3 value when they shout stop. So they clearly get their proportional fair share. And for the last agent, notice that he or she did not shout stop at any point of this process. So her value for all of these other pieces that different other players took can be at most 1/3, because if it was more than 1/3, then she should have shouted stop before that player, right? And if all of these other n-1 pieces are valued at most 1/n for this last player, then her value for her own allocation should be at least 1/n. I mean, you can formalize this argument, but this is the intuitive reason why this is proportional. Now, really moving this knife forward is not something that's allowed in Robertson Webb model, but it turns out that this protocol you can very easily simulate in the Robertson Webb model. Essentially, if you want to find out which player is going to shout stop next, you can just ask a cut query to all the agents, all the remaining agents, and ask them where exactly their value is going to be 1/n from the place where the knife currently is. And so you get this cut mark for each of the agents. This is the mark where they are going to shout stop, and you just choose the leftmost mark, that is the first agent who is going to shout stop. So initially you have to ask all the n agents a single cut query, then one agent leaves, then you ask the remaining n-1 agents a single cut query, then another agent leaves, and so on. So you have sort of n plus n-1 plus ... 1, so you have theta of n squared total queries in the worst case. So this is a very nice and simple algorithm. In n squared queries, it achieves the proportional allocation. The question is whether you can do better. And it turns out that there is another classic protocol called Evan-Paz protocol, and that achieves a proportional allocation using only n log n queries using divide and conquer. So I'll not go through this procedure here. Rather, I'll use another very nice animation by Ariel Pocaccia. So imagine that you have these 4 agents, red, blue, gray, and yellow. And so the first thing that you do is you ask each agent where at what point their value for the cake is exactly half. So for example, for the blue agent, the piece to the left of this and the piece to the right of this are exactly half. For the gray agent, that point appears here. For the yellow agent, that point is here. Right? So you ask this question to each of the n agents. Then you take the halfway mark, right? So in the case of 4 agents, you take the second mark from the left, and you divide the cake here, and you sort of recurse with these 2 agents on the left to the left part of the cake, and these 2 agents to the right part of the cake. And sort of you again ask them, so for example, for the blue and the red agent, we'll ask them where their value for the left part of this cake here is equal to half of their value for the entire, for this entire cake here. And now their order might change, but we don't care about that. One property that this algorithm preserves is that whenever an agent is assigned to some subpart of the cake, their value for the part that they are assigned to is at least half of their value for the cake in the previous level, right? Because here red agent had value half for the part to the left of his red mark and value half for the part to the right of his red mark. And since we chose to cut the cake at the blue mark, certainly his value for the part to which he is assigned is at least half. And for the blue player, his value for this part of the cake is exactly half. Similarly, the gray and the yellow players have value at least half for this part of the cake. If you go one step further and you create this following final assignment, this blue piece that the blue player gets has value at least half of the blue player's value for this part of the cake, which is at least half for the blue player's value for the entire cake. Similarly, if you look at the red player, his value for this allocation is at least half of his value for this part of the cake, which is at least half of his value for the entire cake. And so if you sort of look at this multiplication of half into half, you get 1/4, which is exactly 1 over n that we want to get. So if you have 2 raised to k players, then you have these k levels going here. At each point, the value becomes half, half, half. You multiply it back and you get 1 over 2 raised to k, which is exactly 1 over n. If the number of agents is not a power of 2, then you can still sort of make this protocol work. It requires slight adjustment, but this protocol still gives you a proportional allocation in theta of n log n queries. Okay, any questions about this protocol? Okay, so once we have this, obviously the next question is, can we improve over this as well? And recently, by recent I mean in 2006, Edmonds and Prus showed that any protocol which returns a proportional allocation in this Robertson-Webb model must require omega of n log n queries. So which means that the Evan-Pass protocol is asymptotically optimal. You cannot improve over its query complexity. So the technique is pretty complex, and that's why I did not have any intuition here. I should mention that even though we will not walk through any tedious proofs, wherever the technique has sort of a very nice and clear component, I'll be sure to provide the intuition. But for this, I can refer you to a cake cutting chapter by Ariel Procacha from 2013, and they essentially present the Edmonds and Prus proof in a sort of reasonably understandable, like 2.5 page exposition. So, all right. So the picture for proportionality is very easy. So now let's sort of bump the game up a bit and look at envy-freeness. Again, for 2 agents, we still have the cut and choose. It's proportional, and proportionality for 2 agents is same as envy-freeness, so we get envy-freeness. Turns out that as soon as you move to 3 agents, the problem gets really complex. So there is this protocol by Selfridge and Conway dating back to 1960s, which I'm not going to go over, but here is the snapshot from Wikipedia, and you can see that the protocol is already quite complex, even for 3 agents, and instead of 2 queries for 2 agents, it already makes 14 queries. Now there were later improvements over this protocol which required sort of fewer queries, but all of these protocols still remained sufficiently complex. There is no easy protocol, at least that I know of so far, that you can just describe in a couple of lines. So after this protocol was proposed, for about 3 decades, it was still an open question whether you can have sort of such a nice finite protocol for any number of agents. And then in 1995, Brahms and Taylor proposed the first finite protocol for any number of agents for getting an envy-free allocation. I say finite but unbounded because no matter which valuations you run this protocol on, no matter what the V1 through Vn are, this protocol will always terminate. But if you are trying to ask whether there is a bound on the number of steps that this protocol will require, then there is no bound. You can always find valuations V1 through Vn such that this protocol will make more queries than the bound you were hoping to achieve. Right? So it's finite on every single instance, but the worst case over the instances is infinite. But this was still sort of a significant progress. But after this, it was still a question whether you can even get a bounded protocol for 4 agents. Right? So for 3 agents, there were many protocols proposed, but even for 4 or more agents, it was an open question until very recently, Haris Aziz and Simon McKinsey solved this, and they provided the first bounded protocol for 4 agents, which makes at most 203 queries in the Robertson web model. So, and this was later slightly improved by Amanatidis et al. And they essentially took this protocol and slightly simplified some of the steps so that it only makes at most 171 queries. But there was still sort of this open question whether we can get a bounded protocol for any number of agents n. And this was posed as one of the sort of the big open problems in fair division. I just have some quotes here. So Lindner and Roth in their 2009 treatise on fair division, they said that the development of finite and bounded envy-free cake cutting protocols still appears to be out of reach and a big challenge for the future research. And in 2013, Ariel Prokacha in his book chapter said even further that since 1940s, the computation of envy-free cake cutting protocols the computation of envy-free cake divisions has baffled many great minds across multiple disciplines, including mathematics, economics, and computer science. So settling this problem once and for all is an important challenge for theoretical computer science. And shortly after presenting their 4-agent protocol, Aziz and McKinsey solved this open question where they presented a protocol for any number of agents n, which always returns an envy-free allocation, and it always terminates in a bounded number of steps, although the bound is not quite nice. It's n raised to 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 n. So even for 4 agents, I'm pretty sure that this bound at least is more than the number of atoms in the universe or whatever. So maybe the bound is not nice, but this is still sort of a landmark result, and it received significant media attention. And maybe it will inspire future research where this bound is improved. One thing I want to mention is that it requires these many queries to do a complete allocation. If you are fine with a partial allocation of the cake, well, first of all, with partial allocation, envy-freeness is easy. Just don't allocate anything. Everybody gets 0 value, and it's envy-free. But if you want proportionality and envy-freeness with a partial allocation, then it's again non-trivial. And their protocol can actually stop after order n raised to 2n plus 3 queries and return such a partial allocation. Okay, so this is an upper bound. The question is, what is the lower bound? And the only unconditional lower bound that we know is from Prokacha from 2009, which says that any protocol for finding an envy-free allocation must use omega of n squared queries in the Robertson web model. Yes? It's just the query model, yeah. So, yes, just that. So you can ask an eval or a cut query to any agent in any order, and all you want to do is you want to bound the number of queries that you make in the worst case, no matter what the valuations are, as some function of n. Right. So Fi is just the density, so think of it as sort of a derivative of Vi. So you can get the Vi by integrating this Fi over whatever piece of the cake that you want to find the value for. So for epsilon approximations, you can actually get things somewhat more easily. You can get bounded number of queries, which are a function of both n and epsilon. But before this protocol, the only bounds that we knew were bounds that would go to infinity as epsilon goes to 0. But you can, I don't remember exactly what the bound is for example for epsilon Envy-freeness, but I think it is like n square over epsilon or something like that. But now I mean there is at least a bound that is sort of that is independent of epsilon, right? No, because the Robertson-Webb model doesn't even allow you to access the derivatives, right? It only allows you to make this eval and cut queries. So the derivatives don't even come into the picture here. Yes.
With all these queries, do you get something that is perfect? There is no exchange.
No. So in fact, we'll later see that in the Robertson-Webb model, you cannot even find not just a Pareto optimal, but not even a non-wasteful allocation in finite number of queries. So we'll see that later. Okay. Oops. Okay, so there is this still a big open problem, which is to bridge the gap between this gigantic upper bound and this lower bound. Just to draw some contrast, if you want not just any Envy-free allocation, but rather a simple Envy-free allocation, recall where each agent gets a single interval, then it turns out that such an allocation exists. This is an old result by Su from 1999, but it cannot be computed by any finite protocol in the Robertson-Webb model, even if it's unbounded. Okay, and this is a result by Stromquist from 2008. So if you want simple allocations that are Envy-free, then the problem is provably sort of you cannot do it in the Robertson-Webb model. All right. So with that, let me move to the third property, equitability. So for equitability, here is a nice and simple way to achieve it with two agents. At least there is an existential result. So suppose we want to cut the cake at some point x, and we want to form these two pieces from 0 to x and x to 1, and we want to give the piece from 0 to x to agent 1 and x to 1 to agent 2. Now suppose I take this function f of x, which is the value of agent 1 for her piece 0 to x minus the value of agent 2 for her piece x to 1. Then you can notice that f of 0 is minus 1, because if you put x equal to 0, then agent 1 gets nothing. So this first part is 0, agent 2 gets the entire cake. So this part, second part is 1, so 0 minus 1 is minus 1. Similarly, if you put x equal to 1, then you get f of 1 is equal to 1. So f goes from minus 1 to plus 1, and f is continuous, and that follows from continuity of Vi, which follows from properties of integration. So by intermediate value theorem, there has to be an x star where f of x star is equal to 0, and f of x star being equal to 0 is same as value of agent 1 for her part of the cake being equal to value of agent 2 for her part of the cake, which is same as equitability. Right? So you certainly can have a nice and simple equitable allocation with two agents, and in fact you can sort of turn this into a binary search for x star in the Robertson-Webb model. And this result by Sheshlarova and Pilarova says that you can find an epsilon equitable allocation for two agents using order log of 1 over epsilon queries. And when I say equitable allocation, it means that the value that two agents have for their own pieces of the cake should be at most epsilon different from each other. Okay, in the same paper, they also showed that this technique can be easily extended to n agents to find an epsilon equitable allocation using order n log of 1 over epsilon queries. And then this recent paper by Prokacha and Wang in EC 2017 showed that you can actually get rid of this factor of n even for n agent epsilon equitable allocations. So there is a protocol for n agents which finds an epsilon equitable allocation using order 1 over epsilon log 1 over epsilon queries. So at first this might seem surprising because we are not even querying the valuations of some of these agents. We are only querying the valuations of constantly many agents to find an epsilon equitable allocation. But when you look at how they actually show this, it's pretty simple. So if n is at most 1 over epsilon, then simply use the protocol by Sheshlarova and Pilarova. It requires 1 over epsilon log 1 over epsilon queries, so you are done. If n is more than 1 over epsilon, then let's just choose 1 over epsilon of the agents. Forget about the remaining agents, we'll give them nothing, so they'll have value 0. And these 1 over epsilon agents, we want to give them value at most epsilon. So if these 1 over epsilon agents get value at most epsilon, and the remaining agents get value 0, then it's an epsilon equitable allocation. Now, how do we give 1 over epsilon agents value at most epsilon while still allocating the entire cake? Note that this looks very similar to proportionality. If you have n equal to 1 over epsilon, then epsilon value is exactly 1 over n. But instead of trying to give each agent at least 1 over n value, we are trying to give each agent at most 1 over n value. And it turns out that you can simply run the Evan-Paz algorithm with a slight tweak to compute a so-called anti-proportional allocation, which gives each agent at most 1 over n, or in this case sort of 1 over epsilon value. And in fact, the simple tweak is that if you look at this allocation, at each step we are taking these agents and assigning them to the part of the cake that they value at least half of the previous level. Instead of doing that, we just assign them to the other side which they value at most half of the entire cake. And again, we ask them sort of where is your halfway mark, and we assign them to the part that they value at most half of the previous level. Right? So you do this at most half at each level, and you get an anti-proportional allocation where each agent has value at most 1 over n for their piece of the cake. All right. Yes. Exactly. So this algorithm is, and they in fact sort of clarify this very clearly in their paper, that this is not an algorithm that you want to implement. This is really like a bad allocation, a purposefully bad allocation. They just show this as an argument to say that you cannot hope to prove a lower bound that has n inside it, right? Because there is a protocol, no matter how bad, there is a protocol that achieves an epsilon equitable allocation in these many queries, which is independent of n. So another implication of this is to say that you shouldn't just look at epsilon equitability by its own. Even equitability by its own is a very weak property, right? Because you can have, as we saw earlier, you can have these two agents that value exactly two different halves of the cake, and they might receive the other half that they have 0 value for, right? So you always want equitability along with some other properties, and we'll see that now. So anyway, so the lower bound that they prove is sort of slightly different from their upper bound by a factor of 1 over epsilon and log 1 over epsilon. They show that any protocol for epsilon equitable allocation requires at least these many queries. The important part from here, I think, is that as epsilon goes to 0, this lower bound goes to infinity. So what this shows is that first of all, you cannot have any bounded protocol for finding a perfectly equitable allocation, because if it's a perfectly equitable allocation, this epsilon has to be 0, which means this bound will go to infinity. But more interestingly, they can also show that not just the impossibility of a bounded protocol, there is an impossibility for any finite protocol. So you cannot even have a protocol like Brahms and Taylor's, which on every instance terminates in finite number of steps, but in the worst case it takes infinite number of steps. And this, they do it by essentially slightly modifying some parts of the proof for this lower bound. So here you cannot even have a finite protocol for equitable allocations. So this is, in some sense, in the Robertson-Webb model, equitable allocations are harder to find than envy-free or proportional allocations. Yes?
So is it possible to have a protocol that is epsilon equitable, but meanwhile, like proportional or approximately proportional, like 0.5 proportional?
Right. So I think we are going to look at some of these sort of combinations afterwards, but if I don't recall at least any result that we have here that would answer exactly that question, whether can you have epsilon equitable and let's say proportional or half proportional allocation. Okay. So that's a good question. I'll look into it afterwards, and if I find a result, then I'll amend the slides and put that result in. Otherwise, I'll pose it as an open problem. Okay, so with those three individual properties out of the way, let's first look at the implications of these properties in terms of the price of fairness. So the price of fairness is defined as the worst case loss in social welfare that you must incur because you want to get this fairness property X, right? So social welfare here is just the sum of the values that the different agents achieve. So ideally you want to take each piece of the cake and give it to the agent who has the highest value for this piece. But this can create really unfair allocations where some agents get much more of the cake that they want than some other agents. And so if you impose a fairness property X, then it may restrict you from achieving the highest possible social welfare. And so you can compute the price of fairness for property X as sort of the highest social welfare that you could have achieved in the numerator here over the set of all possible allocations that you could have made, divided by the highest social welfare that you were able to achieve when you imposed this fairness property X. So in the denominator, we only have maximum social welfare across all allocations that satisfy property X. So this sort of gives you the ratio by which you have to sacrifice the social welfare on a given instance, and then you take the worst case over all instances with n agents. Okay. Does this definition make sense? It's the worst case multiplicative loss of social welfare due to imposition of fairness property X. Alright, so here is sort of the work by Karagiannis et al., which studies the price of these three different fairness properties in cake cutting. So they show that the price of proportionality is exactly theta of square root n, which means that in the worst case you will have to lose square root n factor, and you can ensure that you don't lose more than square root n factor. And the price of equitability is higher, it's theta of n. Now the price of envy-freeness is still an open question, because you must lose a welfare of square root of n even to get proportionality. If you want to get envy-freeness, which is a stricter notion, you have to lose a factor of square root n as well, right? So the lower bound of proportionality carries over to envy-freeness, but the only upper bound that we know is n. So there is a gap between square root n and n for the price of envy-freeness. Yes. Yes, yeah. So specifically for this part, if the function is not normalized, then you can just lose infinity, because you can have one agent who has a value of 1 billion for the cake, and you have other agents, or at least sort of theta of n. You'll get at least sort of as bad as theta of n, because you have one agent who has a value of 1 billion for the cake, and you have the other agent who have value epsilon for the cake, and now you have to still give sort of 1/n of the cake to all of these other n-1 agents, and you can only give 1/n of the cake to the first agent who really has all the high value, right?
Is there like a justification? Because I can see that in talk about fairness.
Right.
That we normalize the social welfare, how to justify the normalization.
Right. So in some sense, I mean, there is a very nice article recently by Haris Aziz. It's an open it's an opinion article which normalizes, which justifies the use of social welfare with normalized utilities, and there are multiple reasons, and he really goes into like all the different reasons, but you can either interpret that as a sort of a fair notion of social welfare, where I'm going to look at sort of the sum of the values, but I'm not going to give much more importance to some agent's valuation function than some other agent's valuation function, right? So it's more like sort of one person, one vote kind of principle. Or you can think of it as a sort of a hand-wavy way of preventing manipulations, right? Because if you have non-normalized values and you are trying to maximize social welfare, each agent would just try to bump up their valuation. Instead of saying that my value for the whole cake is 1, they'll say it's 1 million, they'll say it's 1 billion, right? And they'll try to get higher and higher values of the cake, whereas if you use this normalized social welfare, then this incentive at least will go away. They can still misrepresent their valuations, for example, under Dubin-Spanier or Evan-Pass protocols, but it's a slightly sort of more involved manipulation. So he goes into sort of some of these other reasons why you want to care for this, but it's still sort of I would say that there is no sort of one clear reason why this is it, right? You can talk about social welfare without normalized valuations. It's just that most of the results will become very trivial for that. Yes. Right. So we'll until now this is all for deterministic allocations. We'll look at random allocations after this. Yeah. Okay. So that was the implication of these fairness properties in terms of the price of fairness. Now let's look at their interplay with other properties like this non-wastefulness or some sort of economic efficiency, where you don't want to purposefully waste the resources, right? You want to make highest utilization of the resources. So this is not computational efficiency, this is economic efficiency. And one very basic notion of economic efficiency, it's called weak Pareto optimality. This says that allocation A is weakly Pareto optimal if there is no other allocation B that is strictly better for all the agents, right? So you should not have any other allocation B such that Vi of Bi is greater than Vi of Ai for each agent I. Because if there is such an allocation B, why don't you just switch to B instead of staying with A? Right? So this is weak Pareto optimality. It says you can't make everyone happier. Pareto optimality is a slightly stronger notion than this. So allocation A is Pareto optimal if there is no allocation B, such that every agent gets at least as high value as they do in A, and some agent gets a strictly higher value. Right? So instead of having to find this allocation B where everyone gets a strictly higher value, now we just need to find an allocation B where all the agents receive at least as high value and some agent receives a strictly higher value for this allocation to not be Pareto optimal. Right? So achieving Pareto optimality is tougher than achieving weak Pareto optimality. This says that you can't make someone happier without making someone else less happy. Now in isolation, without any fairness properties, even the stronger Pareto optimality is very easy to achieve. You can just run a serial dictatorship. So you can take agent 1, you can say take all the parts of the cake that you have a positive value for. Agent 1 essentially gets the maximum possible value of 1 and leaves. If there are some parts of the cake left which agent 1 had 0 value for, then you bring in agent 2, you say take whatever parts of the cake you have a positive value for and so on, and this you can easily show gets Pareto optimality. But this is certainly not going to be fair because agent 1 gets a lot of the cake and agent 2 might actually be left with nothing. So the question is, what if we want to get Pareto optimality with the other fairness properties that we have studied so far? And it turns out that for two agents, you can actually get Pareto optimality with both the other properties, envy-freeness and equitability. Recall that by themselves, envy-freeness plus equitability was possible through this perfect partition. But now this perfect partition may not be Pareto optimal, but it turns out that you can throw in Pareto optimality and still make it work. And this is a result by Barnabel and Brahms from 2011, and it essentially runs an algorithm that is very similar to a slightly more popular algorithm called adjusted winner that we'll see in the second half of the tutorial. So I'll not go over this algorithm, but you'll see the intuition behind this algorithm in the second part of the tutorial. But this is only for two agents. It turns out that if you want 3 or more agents, then you can't even get Pareto optimality with equitability for a very simple reason. If you have 3 agents and the first 2 agents only want the first half of the cake and the third agent only wants the second half of the cake, then the only way you can have Pareto optimality is to give the second half of the cake entirely to agent 3 and somehow divide the first half of the cake between agents 1 and 2. But in that case, at least one of the agents 1 and 2 will have value less than half, value of less than 1, whereas the agent 3 will have a value of 1. So you can't have all the 3 agents having exactly equal value in a Pareto optimal allocation. So in that sense, equitability is somehow sort of more restrictive because it wants to make sure that no agent receives more value than other agents, regardless of whether their preferences are somehow sort of less strict than the preferences of some other agents. Okay, so you can't get even PO plus EQ together. So the question is, what if we want to get PO plus EF, right? What if we want to get Pareto optimality along with the other fairness property EF Envy-freeness, and it turns out that this you can get. So there is a standard notion called competitive equilibrium from equal incomes. So this is a notion of market equilibrium from economics, but I'll sort of try to make all the economic concepts sort of very easy to understand and diluted. So what this says is that you have these n valuations from the agents, v1 through vn. Given these n valuations, you want to try and find an additive price function p. What this simply means is that think of p as just another valuation over the cake, right? So you want to put a price on every different piece of the cake, and the price is additive. So if you take two disjoint intervals of the cake, the price of these two intervals together is the sum of the price of the two intervals individually. Now you don't just want any price function, you want to find a price function that satisfies the following two properties, and these properties essentially say that each agent should be able to buy their best possible piece of the cake from a unit of fake currency, and when they do this, the entire cake is allocated. So more technically, first we want this sort of the weak competitive equilibrium property. So this is the competitive equilibrium part here. It says that if you take each agent I, and if you take each possible piece of the cake, the subset of 0, 1, then if the price of this piece is at most the price of agent I's bundle, so agent I currently bought this bundle AI, and if this price of this bundle Z was at most the price of the bundle AI, then agent I cannot have more value for Z than their value for AI, because if they had more value for Z, then they would have just bought Z. They have this sort of enough entitlement, which is for this we need to go to the second property, which is equal incomes. This simply says that the price of each agent's bundle is 1, right? So imagine that each agent gets a unit of a fake currency, a new currency that we just give to the agents. So each agent can buy the best possible piece of the cake that they can from a total money of $1, right? And somehow magically we can come up with a partition of the cake into this disjoint pieces A1 through AN, such that A1 is the best possible piece that agent 1 can buy from his total value of $1. A2 is the best possible piece that agent 2 can buy from his entitlement of $1, and so on. So it's not even clear that you can always find such a price function and such an allocation where such a nice thing happens. But a classic result of Valor shows that for cake cutting, a CEI allocation always exists. So there is always an allocation AI for which there is such a price function P. Further, every CEI allocation is both envy-free and weak Pareto optimal. So the existence part here is the tricky one. Once you know that such an allocation and a price function exists, envy-freeness and weak Pareto optimality is very easy. Why do we have envy-freeness? Because note that the price of some other agent's allocation AJ is also 1, right? The price of every agent's bundle is 1. So if the AJ had a price of 1, agent I could have bought AJ, right? Price of AJ is at most, in fact it's equal to the price of AI. So that means VI of AJ should be at most VI of AI, right? Agent I could have bought some other agent's bundle as well. It also had a price of 1, and if it could have bought it, and if it had a higher value, she would have bought it, right? So if you can find such an allocation, it is easily envy-free. It is also weakly Pareto optimal, because if you can find a different allocation B such that every agent has VI of BI greater than VI of AI, then the price of that BI should be greater than the price of the AI, which is 1, right? So the price of each BI has to be more than 1, but then if you sum up all the prices of the different BIs, then the price of the entire cake is more than n, which is impossible because the price of the entire cake is also the sum of the prices of the different AIs, which is equal to n. So yes. 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 Yeah. So it's only the best piece out of a price limit of 1, where the price is computed as a function of the valuations themselves. Mm-hmm. So if you choose one of the AIs, so if you look at sort of all the possible pieces of the cake that have price at most 1, AI is going to be the piece that agent I has the highest possible value for. No, there are infinitely many pieces. I mean, I'm not only looking at the pieces that are AI, AJ, AK, or so on. I'm looking at all possible subsets of the cake that have price at most 1. Agent I has the highest value for AI among all such subsets of the cake. Yeah, for every Z that is a subset of the entire cake. I mean, really a finite union of disjoint intervals. All that restriction still comes here, but it's not just Z that is AJ or AK for some other agent's allocation. Any other questions? I mean, this is a concept that takes some sort of derives some of the other concepts from economics, so it might be sort of harder to grasp at first, but so please feel free to ask questions. Yes. This price may not be unique, not here. We'll see. Yeah, that's true. That's true. But here is a slightly stronger notion of a competitive equilibrium where almost all of those uniqueness properties will hold. Okay. So this was actually proposed in a very recent paper by Segal Halevi and Ziklai, and I mean the way I think of it is that this is the way CEI should have been defined, but it wasn't defined in this manner earlier because this is instead of weak Pareto optimality, first of all it gets the actual Pareto optimality, and it has all of these uniqueness properties. Right? So what they did is that, so let me just focus on this sort of stronger competitive equilibrium property. Instead of saying that among all the pieces that I could have bought from a $1 currency, I'm getting the highest value piece, it's saying that if you look at any piece of the cake, Z as a subset of 0, 1, and if you look at any subset of the piece that I am being given, so some Zi which is a subset of AI, and if you compute the bang per buck, so if you look at the value that agent I has for Zi divided by the price of this subset Zi, it has to be at least as large as the agent I's value for Z divided by the price of Z. So the value divided by price is sort of called the bang per buck. So agent I is only interested in getting pieces of the cake that she has the highest bang per buck for. Now, how is this different from the previous allocation? Well, in here, agent I could have been given a piece of the cake that she actually has a 0 value for, and what happens, right, so here agent I could have received a piece of the cake that she has 0 value for. It's just that the rest of the allocation that is given to agent I has such a high value for agent I that she cannot buy any other thing from the price of at most 1. And here we cannot give to an agent a piece of the cake that she has 0 value for, because for that piece the bang per buck would be 0, and for some other pieces that she is actually receiving which she has some value for, the bang per buck would be positive, right? Because the value of agent I for at least some of the allocation that she is receiving is positive, and the price for that is positive, so the bang per buck for some part of her allocation is positive, so the bang per buck for the remaining part of her allocation cannot be 0. And so because of this, so they show first of all that an SCEI allocation also exists, and every such allocation is both envy-free and Pareto optimal rather than just weak Pareto optimal. And the reason you get Pareto optimality is now if you look at an allocation B which gives at least as much value to all the agents and a strictly higher value to some agent, then you can even say that for the agents I who are getting at least as much value, the price of this BI has to be at least 1. This you could not say earlier in this property, because if agent I is getting exactly the same value under BI as under AI, you have no idea what the price of BI is. It could be strictly less than 1. Whereas here you know that the price of BI has to be at least 1 if agent I is getting at least the same value, and if agent I is getting a strictly higher value, then the price of BI must be strictly higher than 1. So if you add up the prices of all the BIs, you still get strictly more than n, which would lead to a contradiction. So the only sort of thing that I want you to remember from this is that there was an earlier notion of competitive equilibrium from equal incomes, which gave envy-freeness and weak Pareto optimality, and did not have several of these uniqueness properties. And there is a more recent sort of this stronger notion of competitive equilibrium from equal incomes, which has the stronger notion of Pareto optimality, and in fact it has uniqueness properties. So first of all, there is only one possible, so there could be several different allocations that are strong CEI, but they all give the same utility to a given agent. So agent I is going to get the exact same utility under all of these different SCEI allocations. And further, an allocation is SCEI, which means that there is such a price factor if and only if it maximizes the Nash welfare or the product of the values of the agents. So you can in fact forget about all of this price stuff, and you can just focus on finding an allocation A which maximizes the product of the different values of the different agents for their own allocation. So instead of maximizing the sum, here you want to maximize the product. And this result shows that the set of SCEI allocations coincides with the set of Nash optimal allocations. Okay. So let's just see very quickly what this Nash optimal rule does. So imagine this example where you have two agents. Agent 1 wants the first 2/3 of the cake uniformly and doesn't care about the rest 1/3 of the cake, and agent 2 values the entire cake uniformly. Again, I have set this value 1.5 such that if you do the integration for this 2/3 part, it turns out to be 1. Okay, so we know that the Nash optimal allocation has to be Pareto optimal. I mean, we know that because it coincides with SCEI, which is Pareto optimal. Okay? So because it's Pareto optimal, we know that agent 1 has to get some x fraction of the piece of the cake that she likes from 0 to 2/3, and agent 2 gets the remaining 1 minus x fraction of this part, and all of this remaining part from 2/3 to 1. Right? Certainly 2/3 to 1 has to go to agent 2 for Pareto optimality. So if you compute the value of agent 1 for the piece of the cake that she gets, it's exactly x. It's the x fraction of the part of the cake that she wants. And the value for agent 2 is this 1 minus x fraction of this length 2/3 that she wants, and this length 1/3 she is getting completely. Okay, so that's simplifies to 3 minus 2x by 3. Now if you want to maximize the product of the values of the two agents, you maximize x times 3 minus 2x by 3 over x ranging from 0 to 1, because x is a fraction, it's not the interval 0 to x, it's the interval 0 to x times 2/3. Then you get that the optimal is achieved at x equal to 3/4. So the Nash optimal allocation gives the interval from 0 to 3/4 times 2/3, which is exactly half. The interval from 0 to half to agent 1, and the interval from half to 1 to agent 2. Now this allocation, you can check it's envy-free and Pareto optimal, but it is not the only envy-free and Pareto optimal allocation. For example, you could have just given the piece from 0 to 1/3 to agent 1 and the piece from 1/3 to 1 to agent 2. Agent 1 wouldn't have envied agent 2 because she gets half of what she wants. The other agent also has half of what she wants, and it's also Pareto optimal. But that's not the allocation that the Nash optimal rule chooses. It chooses a very specific envy-free and Pareto optimal allocation. All right. So that is all I want to say for Pareto optimality. Let's move on to strategy proofness, which is the incentive property or the manipulation part that we referred to earlier. So for this, I would like to move to a different model. Rather than the Robertson-Webb query complexity model, we want to look at direct revelation mechanisms. So forget about how many queries we have to make. Suppose we have access to the entire valuations V1 through Vn, So we get these valuations in some format. We are maybe able to see the entire curves. It requires infinitely many bits, but we don't care. And now we just want to return an allocation A. So if the function is denoted by h, let's say that h of v1 through vn is A, and the piece of the cake that agent I gets, AI, suppose that it's outcome of some function hi. Now strategy proofness for deterministic mechanism says that, so it's a direct revelation mechanism in this framework is strategy proof if no matter what the agent's valuations are, so no matter what the v1 through vn are, and no matter which agent I you focus on, and no matter which false report vi prime that agent I could submit instead of her true valuation vi, if you look at the value that agent I gets in the piece of the cake that she is allocated when she reports her true value vi, it's at least as much as the value that she would have gotten if she had reported some false valuation vi prime. So no matter what the other agents are doing, no matter what their valuations are, no matter what they are reporting, agent I is always at least weakly better off by reporting her true value than by a false value. So this is a very strong notion of incentive compatibility, truthfulness. There are many names in the literature for this notion. But we will use strategy proofness, or SP for short. Now we can also talk about randomized mechanisms. For this, there are several different notions of strategy proofness that you can define. Here I want to focus on strategy proofness in expectation. So this simply means that all of the previous definition stays as is, but instead of saying that agent I gets at least as much value in the true case as in the false reporting case, we want to just replace the value by expected value, where the expectation is over the randomization of the mechanism. Okay. So now imagine that the agents are so-called risk neutral, so they only care about their expected value and not the variance. So we don't want the agent to be able to gain in terms of the expected value by misreporting her valuation. So that is strategy proofness for randomized mechanisms. So the question is, what can we get in terms of the Pareto optimality or the fairness properties, the Envy-freeness, proportionality, and equitability, if we want to do it in a way that the agents cannot manipulate. So for deterministic mechanism, this recent result by Menon and Larson shows that no deterministic SP mechanism can even get approximate proportionality. Certainly cannot get exact proportionality, but can't even get half proportionality or 1/3 proportionality. And since envy-freeness is at least as strict, you also cannot get envy-freeness with a deterministic strategy proof mechanism. Okay. What about Pareto optimality? Well, if you just want to get Pareto optimality with strategy proofness, it's easy. You just run the serial dictatorship that I mentioned earlier, give agent 1 or whatever part of the cake she has a positive value for, then among the remaining parts of the cake, give agent 2 whatever she wants, and so on. That is going to be both strategy proof and Pareto optimal. It's very easy to see that. So if this is possible, let's try and add some property to strategy proofness plus Pareto optimality. Certainly cannot add envy-freeness or proportionality because that's infeasible all by itself. So let's try to add equitability, but the problem is we already saw an example where you can't get Pareto optimality and equitability together. So you can't have that as well. So the next question is, what if we forget about Pareto optimality and we just want to get equitability? And that's apparently an open question, whether there exists a direct revelation deterministic strategy proof mechanism that always returns an equitable allocation. So that is the picture for deterministic strategy proof mechanisms. You cannot get proportionality, you cannot get envy-freeness. It's not clear whether you can get equitability. You can easily get Pareto optimality, but you can't get Pareto optimality along with any of the other fairness properties. Okay, what about randomized mechanisms? So when I say randomized mechanisms, we just want the strategy proofness part to hold with expected utilities. I want the fairness and efficiency properties to hold for every allocation that this mechanism might return with any positive probability. Okay, so I don't want the envy-freeness to hold in expectation, I want the envy-freeness to always hold. Okay, so in this case, again, PO plus EQ allocations may not exist, So you cannot get both of them with strategy proofness. So you have to drop either at least one of these, and you can potentially add EF to this. So you can either hope for SP plus PO plus EF, or you can hope for SP plus EF plus EQ. Again, the first one here is an open problem. So it's not clear if you can get a randomized strategy proof in expectation mechanism that always returns a PO plus EF allocation. In fact, the only reasonable mechanism that we know which returns a PO plus EF allocation is this Nash optimal rule. And the Nash optimal rule is not strategy proof. So my conjecture would be that the answer here is likely no, but this is still an open problem. But the second combination, remember that EF plus EQ is possible by a perfect partition. And it turns out that you can actually use perfect partition to get strategy proofness in expectation as well. And this is a result by 2 independent papers. They show that there is a randomized SP mechanism which always returns an EF plus EQ allocation, and the method is very simple. You simply ask for the allocations, ask for the valuations, you compute a perfect partition B. Recall that this is the partition where each agent's value for each piece of the partition is exactly 1 over n. And now you just randomly assign these n pieces to the n agents uniformly at random. Okay, so each agent gets each piece with probability 1 over n. Now this is strategy proof because regardless of what you report and regardless of how this sort of perfect partition is computed, and it may not even be perfect according to your true valuation because you have reported something false, the cake is being divided into n pieces and you are going to get each piece with probability exactly 1 over n. So your expected value for this randomized allocation is 1 over n times your value for the entire cake, which is always 1 over n. So because you are getting each piece of the cake with probability 1 over n, no matter what you do and no matter what these pieces are, your expected value from this mechanism is always going to be exactly 1 over n, no matter what valuation you report. So you certainly cannot gain by misreporting your valuation. And assuming that the agents report their valuations correctly, this is always taking a perfect partition and assigning the pieces in some arbitrary manner, and that's always going to be envy-free. Because you get a piece that you have a value 1 over n for, somebody else gets a piece that you also have a value of 1 over n for, and so that is both envy-free and also equitable. Okay, so oops, this is my, yeah. So this is the summary of all the sort of existential results. I have not included the computational results, how many queries you need to achieve different combinations, but here is the summary of all the existential questions. Clearly, whatever you cannot get by whatever you cannot get even by randomized mechanisms, you also cannot get by deterministic mechanisms. So I have not listed that. Whatever you can get by deterministic mechanisms, you also can get by randomized mechanisms, because every deterministic mechanism is by default randomized as well. So I have not listed that, and the question marks are open problems. And obviously, if something is achievable, so for example, if you look at this tick over here for randomized mechanisms for this combination, then if you just want a subset of those combinations, it's also going to be a tick. So positive results will carry over when you only want a subset of the properties, and negative results will carry over when you want a superset of the properties. Right? This sort of at least gives a summary of those results. Okay, with the remaining last few minutes before we break for the coffee break, I'll just go over some sort of some extra topics that we weren't able to devote too much attention to. One such topic is the case of restricted valuations. So until now we were allowing any sort of valuations that these agents might have. One interesting special case is piecewise constant density function, where essentially the density function looks like this. So you have some constant until some point, then it jumps, then you have constant, then it jumps, then you have constant, and so on. And one special case of even this special case is piecewise uniform density function, where all of these non-zero values that you see have to be exactly the same. So essentially there is some subset of the cake that you want uniformly and the rest of the cake that you don't care for. So it turns out that if you have piecewise uniform valuations, which is the most special case, then you can actually get strategy proof deterministically along with EF plus PO. And so recall that in the general valuations, you can't even get strategy proofness plus EF deterministically. And if you have piecewise constant valuations, then for that you can compute this sort of Nash optimal allocations in polynomial time by taking essentially this direct revelation. So this is not in Robertson-Webb model, rather you just want the agents to directly report the sub-intervals for which they have a positive value. And here is an interesting result by Kurokawa et al. It says that if you have an algorithm to compute an envy-free allocation for n agents with this most restricted piecewise uniform valuations, which has a bounded number of queries, some g of n, then you actually have an envy-free, the protocol for an envy-free allocation for general valuations using the same bound at most g of n. So in some sense this says that if you are trying to get envy-free allocation, forget about general valuations, just design a protocol for piecewise uniform valuations. If you have done that successfully, you have a protocol for general valuations as well. And this result, essentially the idea of the proof is as follows. So let the same protocol interact that you have for piecewise uniform valuations, let it run on general valuations, and let it make some number of cut and eval queries in the Robertson-Webb model. After any number of queries, you can create piecewise uniform valuations that would have responded in the exact same way to these queries, and the value that each agent places on their own piece of the cake at the end of this protocol is exactly same under these piecewise uniform values and the more general values. And this key sort of construction is enough to show that the protocol will also terminate in at most gn queries for general valuations. And as I mentioned earlier, if you want Pareto optimality, you actually cannot get it in Robertson-Webb model, not even Pareto optimality, even on non-wasteful allocations for these piecewise uniform valuations. Okay, and the final, if I just can hold you for one more minute, the final topic is this burnt cake division. And so think of this as a cake, but the cake is burnt. So the agents really don't want to eat this cake. They have a negative value for eating this cake rather than a positive value. But you have gone to a birthday party and you don't want to upset the host, so you still have to finish the entire cake. So the entire cake still has to be divided among the agents, but agents are trying to avoid the cake as much as possible. Still different agents have different sort of disutility for eating different parts of the cake. So you still have these heterogeneous valuations. Now what can you do? So at first point, you might think that this is exactly the flipped version, right? You can just take all the protocols, just run them on the negative values, and you are done. And it turns out that for equitability and perfect partitions, this is fine, because these definitions are defined by equality. And so you can just simply run the same protocols with the negative FIs and negative VIs, and you still get equitability and perfect partitions in this burnt cake model. But envy-freeness is not so easy. And so this recent paper by Peterson and Su give the first finite but unbounded protocol for envy-free allocations with n agents in the burnt cake model. And they essentially take the Brahms-Taylor protocol and sort of convert each of its steps to the burnt cake version rather than the good cake version. But certain operations here require some non-trivial transformations. And so open problem is to essentially solve the problem that Aziz and McKinsey solved for the good cake model, which is whether there is a bounded envy-free protocol for the burnt cake. Okay, so here is another model that is sort of somewhere between burnt and good cake. So what if you have some items that agents could have positive or negative values for? It's not all positive, it's not all negative. So again, you have these items, and each agent has this value Vi of Oj, and which can be positive, 0 or negative. And the values are still additive if you give sort of different fractions of these items to different agents. And so here, sort of I won't go over this detailed slide, but this recent result by Bogomolnaya et al. Shows that you can still compute a CEI allocation, and it is still envy-free and Pareto optimal. So you know that an envy-free and Pareto optimal allocation exists. And unlike the good case, the utility profile in this CEI allocation may not be unique anymore, right? So remember that in the goods case, The only way you get this CEI is by maximizing the Nash welfare, and in all such allocations, a given agent gets the same utility. Here, that is no longer true. There can be exponentially many different utility profiles where this happens. So this shows a fundamental divide between the goods model and the goods plus bads model. So that's it. Here are some things that we were not able to cover, so Nash equilibria of cake cutting protocols when they are not strategy proof. Looking at optimal cake cutting, so subject to some fairness condition. What if you want to maximize social welfare? We looked at the price of fairness, but how do you actually algorithmically do that? The number of cuts and the geometry of the actual cuts that we did not really look at in detail. We did not look at multidimensional cakes and how to really divide them, or we did not look into detail into randomized and or strategy proof algorithms in the Robertson-Webb model. We looked at strategy proofness in the direct revelation, but there is some work here as well. And we also did not look at non-additive valuations, but here are the references for the papers that we did look at. So in case you want, you can find these slides afterwards on the website.